Hello everyone. I am excited to introduce you to our work on privatized robotic exploration with deadlines. Most exploration techniques focus on exploring the complete environment and do not consider exploring the unknown environment with deadlines. However, when there are time constraints imposed due to the hazards of an unknown environment, such as fire or radiation, it limits the time the robot can explore the environment. Similarly, the battery itself can impose a deadline on the robot. Due to the imposed deadline, we cannot explore the entire environment, so we have to resort to a privatized exploration by privatizing certain regions of the environment. The goal is to identify the layout of the environment, and the robot should come back to the home position by the end of the deadline. This presentation is a conceptual overview. Please read the paper for more details. We consider modeling the exploration problem as an orienteering problem. The objective of the orienteering problem is to maximize the price collected along a path within a deadline. Vertices represent physical locations in the exploration environment. On the graph on the right, each vertex has an associated price based on the building structure identified at the vertex. The robot starts from the home vertex. The price at the home vertex is considered as 0 as it is already visited. Each edge's weight is based on the estimated time it takes for the robot to traverse between the vertices. Here we have a deadline of 50 time steps. The solution to our orienteering problem would give us a path that starts from the home vertex, goes through vertex B, then A, and finally back to the home vertex. The path cost adds up to 50. Note that due to the limited deadline, the robot could not visit vertex C. When the algorithm is used for exploration, the solution is recomputed when the robot reaches vertex B. When the deadline is larger than the time required to visit all the vertices, orienteering problem might not provide us with the shortest path to visit all the vertices. Here we have a deadline of 100. The orienteering problem generates a path with a path cost of 66. This is not the shortest path possible in the graph. The profitable tour problem addresses this drawback by maximizing the difference between the price collected and the trajectory cost. On the right, we have an example with a deadline of 50 time steps. Here, the profitable tour problem solver and the orienteering problem solver generate the same path. So even when the deadline is much larger than the time taken by the robot to visit all the vertices, the profitable tour problem provides us the shortest path to visit all the vertices. Here we have a deadline of 100 time steps. The profitable tour problem solver computes a path of 63 steps, which is shorter than the path generated by the orienteering problem. Note that even though it finds the shortest path, the first vertex it visits is a lower price vertex. We compared the previous two exploration algorithms with the priority-based greedy algorithm. Here the robot visits the highest priority vertex available that can be visited within the deadline, while ensuring the robot can return to the home vertex. On the right, we have a deadline of 50 time steps. The robot selects vertex B to visit, as the robot can visit vertex B and return home within the deadline. Here are the graph environments for experiments. We tested on 6 different graph environments carefully modeled on different types of indoor environments and corridor layouts. Here are the plots for selected graph environments. P-greedy is the priority-based greedy algorithm, C-greedy is the cost-based greedy algorithm, OPE is the orienteering problem-based exploration algorithm, and PTPE is the profitable tour problem-based exploration algorithm. On the x-axis we have the deadlines, and on the y-axis we have percentage of environment explored. Note that the priority-based greedy algorithm performs competitively and sometimes outperforms other algorithms with a low operational overhead. Here are the 3 gazebo environments used for testing. Each of the gazebo environments is modeled on a corridor shape observed in buildings. Most buildings have a combination of such elemental layouts of corridors. The results on the gazebo environments are shown as bar plots. Here, longer bars means better results. On the top left, in the straight corridor environment, the profitable tour problem-based exploration performs better for 1500 seconds and 1000 seconds. However, for short deadlines like 500 seconds, the priority-based greedy algorithm outperforms the other two algorithms. In the other two environments, notice that the algorithms perform similarly. To conclude, we have discussed three privatized exploration algorithms whose goal is to compute the geometric layout of an initially unknown environment within a deadline. The privatized exploration algorithm was formulated as an orienteering problem and a profitable tour problem and tested on graph and gazebo environments. The priority-based greedy algorithm performed better on graph environments, and all the algorithms performed similarly on gazebo environments. Our future work is divided into two parts: further testing in additional gazebo environments and the real world, and to obtain vertex price values based on semantic information from cameras. Thank you for watching this video. If you have additional questions, feel free to reach out by email.